In this video, we're going to learn how to solve systems of first-order linear differential equations using eigenvalues and eigenvectors. We'll cover all three cases: distinct real eigenvalues, repeated eigenvalues, and complex eigenvalues. And I'll work through a full example for each one so you can see exactly how the method works in practice. Let's get started. We're going to begin by walking through the 4 steps that we need to follow to find a general solution to a 2x2 system of differential equations that looks like this. dx dt is equal to ax plus by, and then dy dt is equal to cx plus dy. When we walk through our examples, we'll put in numbers for a, b, c, and d. When you solve a system like this, the first thing you need to do is to write the system in matrix form. We're going to write it like this. The derivative of vector x with respect to time is equal to matrix A times vector x, where vector x is equal to xy, it's right up here, and matrix A, which is A, B, C, D, and that's right up there. Vector x right here is the solution to our system of differential equations. To find the solution form for x, what we're going to do is we're going to compare our system dx dt is equal to ax to the differential equation du dt is equal to lambda u. Now, these two are different, but their solution forms are similar. The solution to the differential equation du dt is equal to lambda u is equal to a constant c times e to the lambda t. Similarly, solutions to our system of equations dx dt is equal to a times x is going to be of the form x of t is equal to vector v times e to the lambda t. Lambda is the eigenvalue of matrix A, and then v is the eigenvector that is associated with that eigenvalue. Each eigenvalue lambda is going to produce a solution in this form right up there, and then the general solution of our system is going to be a linear combination of those individual solutions. The second step that we need to follow to find our solution x is to find the eigenvalues. To do that, we are going to solve the equation, the determinant of a minus lambda I is equal to 0, and we're going to solve that for lambda. If A is a 2x2 matrix, like the one that we're working with, alternatively, you can solve the equation lambda squared minus the trace of A times lambda plus the determinant of A is equal to 0. The trace of A is just when you add up the main diagonal elements in matrix A. In step 3, we're going to find the eigenvectors. An eigenvector v is a non-zero vector that satisfies this equation AV is equal to lambda v. If we move the lambda v to the left, that's equivalent to solving the system of equations a minus lambda I times v is equal to 0. And we'll solve that for v. The last step, step 4, is to write down the general solution. The form of the general solution is going to depend on what type of eigenvalue we got in step 2. It's going to be either distinct real, repeated, or complex. Let's look at the solution for case 1, where our eigenvalues are distinct real eigenvalues. So we're going to let lambda equal lambda 1 and lambda 2. Our solution then looks like this. Our v's are our eigenvectors, and then our lambdas are up in the exponent. The second case you can encounter is when lambda is a repeated eigenvalue. I just put down here that this is the case where lambda is equal to lambda. Here's what our solution looks like. We have one eigenvector v that appears in both of these terms. We have our eigenvalue up here in the exponent. And then we have a new vector that we're going to call vector W, and it is called a generalized eigenvector, and you find it by solving this equation. The last case is where we have complex eigenvalues, and we're going to let lambda equal alpha plus or minus beta times I. Here's what our solution looks like. Let's start with the exponent. Alpha is up here in the exponent, and then beta is in the trig functions. Now let's think about our eigenvector. Our eigenvector is vector v, and we have to split it up into its real part and its imaginary part. A is the real part, and it's right up here in our solution, and then b is the imaginary part, and it's right here in our solution. Let's now look at some examples. We're going to walk through an example where we're going to be solving a system of first-order linear differential equations for the case where we have distinct real eigenvalues. We're going to find the general solution to the system of equations dx dt is equal to x plus 3y and dy dt is equal to 4x plus 2y. The first thing that we're going to do to solve this system of equations is to write the system in matrix form. We're going to let vector x have the components xy. This enables us to write our system like this. We have d dt of xy, and then on the right-hand side, we are going to separate the constants from the x and the y, and we're going to write it as a matrix 1, 3, 4, 2. Let me go up here and show you where that comes from. There's the 1, we have the 3, the 4, and the 2, and then we multiply this by x times y. This gives us the linear system, the derivative of vector x with respect to time is equal to what we call a matrix A times vector x. And we'll write down that matrix A is equal to 1, 3, 4, and 2. The next thing that we want to do is find the eigenvalues. To do this, we need to solve the equation determinant of a minus lambda I is equal to 0. Alternatively, we can solve this equation, lambda squared minus the trace of matrix A times lambda plus the determinant of A is equal to 0. I'm going to solve it both ways so that you can see how each works and then choose the one that's going to work best for you. We have our determinant, and then we're going to subtract off lambda from our diagonal elements. So this is going to give us 1 minus lambda, 3, 4, 2 minus lambda is equal to 0. When we find the determinant, we multiply the main diagonal elements, 1 minus lambda times 2 minus lambda, and then we subtract off the off diagonal elements, which is 3 times 4, and that's equal to 0. This gives us lambda squared minus 3 lambda plus 2 minus 12 is equal to 0. So we have lambda squared minus 3 lambda minus 10 is equal to 0. Now, before I find lambda, let's go over here to the right, and I want to show you how we're going to get the same equation using the trace and the determinant. This gives us lambda squared minus the trace of A. Let's go back up here and let's look at this. If we look at matrix A, the trace is going to be when we add the main diagonal elements. So this is going to be 1 plus 2 times lambda, and then we have the determinant of A, which is going to be the main diagonal elements multiplied, so that's 2 minus 3 times 4 gives us a minus 12. And that's 0. So we get the same equation. Lambda squared minus 3 lambda minus 10 is equal to 0. I think this is easier, but the hard part is you have to remember this equation right here. Let's go down here and let's go ahead and let's factor this. We can factor this as lambda minus 5 and lambda plus 2 is equal to 0. So this gives us lambda is equal to 5 and lambda is equal to minus 2. I'm going to let lambda 1 be equal to 5 because that's the biggest eigenvalue and it's called the dominant eigenvalue. And then I'm going to let lambda 2 be the other one, which is minus 2. Now, before we go to step 3, we have to look at these eigenvalues and note what type they are. These are distinct real eigenvalues. Knowing this is going to enable us to choose the correct form for the solution. Step 3 is to find an eigenvector associated with each of our eigenvalues. To find the eigenvector, here's what we're going to have to solve. We're going to need to solve the system A minus lambda I times our eigenvector V is equal to 0. Let's just put from our previous page, our matrix A was 1, 3, 4, 2. And I am going to let vector V, just to make things easy, be equal to AB. Let's go ahead and let's set this up in general. We have A minus lambda I, so this is going to be 1 minus lambda, 3, 4, 2 minus lambda. You're just subtracting off lambda from the main diagonal entries. And then our vector V is AB, and it's going to be equal to the 0 vector. Now we're going to go ahead and we're going to find an eigenvector associated with each eigenvalue. Let's first let lambda be lambda 1, which is equal to 5. So this gives us 1 minus lambda. So this is 1 minus 5. We have 3, 4, 2 minus 5 times AB, and that's equal to 0, 0. This reduces to minus 4, 3, 4 minus 3 times AB, and that's equal to 0. You can solve this using linear algebra, but I'm going to solve it using just regular algebra in case you haven't had linear algebra yet. The system becomes minus 4a plus 3b is equal to 0. That's our first equation. And then our second equation is 4a minus 3b is equal to 0. Notice that these two equations are the same. So we're just going to go ahead and we're going to solve for one of them. And we get a is equal to 3/4 times b. Now what we have to do is choose a value for b so that we can also get a value for a. That's why let's go up here to the top and look at something. Do you see this word "and" right there? It says find an eigenvector, not find the eigenvector. The reason it says that is we are going to choose a value for b, and there are an infinite number of values that we could pick. And that's why there are an infinite number of eigenvectors. And we just need to find one. I'm going to make this as easy as we can. So what I'm going to do is I'm going to let b equal 4. And that's going to tell us then that a is equal to 3. That way we don't have fractions in our answer. This gives us that vector v. That's our eigenvector. We're going to call it vector v1 because this is going to match our eigenvalue lambda 1. And remember, it was equal to AB, and we now know that this is equal to 3 and 4. I'm going to highlight this because we're going to need this in a minute. Now we're going to find our second eigenvector, so we're going to let lambda be lambda 2, and that was minus 2. We are going to be looking right here, and lambda is negative 2. So we're going to end up adding 2 to the diagonal entries. This gives us 1 plus 2, 3, 4, and then 2 plus 2. This multiplies AB. It's a different AB than we had for our first eigenvalue. And we get 0, 0. This gives us 3, 3, 4, 4 times AB, and it's equal to 0, 0. This gives us the equations 3a plus 3b is equal to 0, and then 4a plus 4b is equal to 0. So this is the same equation, and we get that a is equal to minus b. I'm going to let b be equal to -1, and that means that a is going to equal 1. I just like it when the first entry in our vector is positive. I just think it makes it easier. So v2 is equal to ab, which we now know is 1 minus 1. And we'll highlight that. Now we come to our last step. That is to write the general solution. Because we have two distinct real eigenvalues, our general solution looks like this. Our eigenvalues are up here in the exponent, and then our eigenvectors are right there. Our general solution then is x of t is equal to c1 times v1. Let's go back up here. v1 is 3, 4. Times e to the lambda 1. Lambda 1 was 5, so that's 5t. And then we add on c2. Our v2 is 1 minus 1 times e to the lambda 2t, and lambda 2 was minus 2, so we have minus 2t. And there's our final solution. We're going to now walk through an example where we're going to solve a system of first-order linear differential equations for the case where we have repeated eigenvalues. We're going to find the general solution to the system of equations dx dt is equal to 5x minus y, and dy dt is equal to 4x plus y. The first thing that we want to do is we want to write this system in matrix form. We're going to let x be equal to xy, and this gives us the derivative with respect to time of xy is equal to 5 minus 1, 4, 1. That's just separating our constants from our x and our y, and we're going to multiply that by x times y. We can then write this as d vector x dt is equal to a matrix A times x, where matrix A is equal to 5 minus 1, 4, 1. In step 2, we are going to find the eigenvalues. These are the eigenvalues of our matrix A. There are two ways that we can find them. The first way is to solve the determinant of a minus lambda I is equal to 0. And then the second way is to solve it using this equation. Lambda squared minus the trace of a times lambda plus the determinant of a is equal to 0. We'll solve it both ways. Let's go over here and do the determinant way first. We're going to take 5, and then we're going to subtract lambda off the main diagonal, and then we have a minus 1, 4, and then we have a 1 minus lambda, and that's equal to 0. Multiplying the main diagonal entries, we have 5 minus lambda times 1 minus lambda, and then we subtract off our off-diagonal entries, minus 1 and 4, and we multiply those. This gives us lambda squared minus 6 lambda plus 5 plus 4 is equal to 0. This gives us lambda squared minus 6 lambda plus 9 is equal to 0. Before we go to factor this, let's go over here to the right and let's do it the second way. This gives us lambda squared minus the trace of a. Here's what the trace is. You take the diagonal entries and you're going to add them. So this is 5 plus 1 times lambda. And then for the determinant, you multiply the main diagonal entries and subtract off the off-diagonal entries multiplied. This gives us lambda squared minus 6 lambda plus 9 is equal to 0. This way is probably a little bit quicker, but it does have a drawback because you have to remember what that equation is. Let's now go down here to the left and let's factor this and find lambda. We can write this as lambda minus 3 times lambda minus 3 is equal to 0, and we get lambda is equal to 3 and 3. Before we go on to the next step, let's make a note at what type of eigenvalue we just got. The eigenvalues in this example are called repeated eigenvalues. This is going to tell us what our general solution is going to look like. In step 3, we need to find the eigenvector associated with our eigenvalue. Let's just make a note that our eigenvalue is lambda is equal to 3. To find the eigenvector, we have to solve the system of equations a minus lambda I times v is equal to 0. Let's also put over here what our a was. From our last page, it was 5 minus 1, 4, 1. And then we're going to let vector v be ab. We're going to subtract lambda off the diagonal, so we get 5 minus lambda minus 1, 4, 1 minus lambda. And we're going to multiply this by vector v, which we just saw was ab, and it's going to be equal to 0 on the right-hand side. Now we're going to substitute in that lambda is equal to 3. So we get 5 minus 3 minus 1, 4, 1 minus 3, and we multiply this by ab, and it's equal to 0. This gives us 2 minus 1, 4 minus 2 times AB is equal to 0, 0. We can solve this using linear algebra, and we can also solve it just using regular algebra, and I'm going to solve it using regular algebra in case you haven't had linear algebra yet. This gives us 2a minus b is equal to 0, and then we have 4a minus 2b is equal to 0. These are the same equation. I'm going to solve this for a because I think that's going to be easier. A is going to be equal to b over 2. Now we get to choose a value for b. So I am going to let b be equal to 2. And the reason I'm doing that is that makes a equal to 1, which is really nice. Our solution then, our eigenvector, is equal to AB. And now we can plug in that this is equal to 1 and 2. We're going to need that in a minute, so let's go ahead and let's highlight that. Now let's go to step 4. Step 4 is to find what's called a generalized eigenvector. And that generalized eigenvector we're going to call vector W. So we're going to solve the system of equations a minus lambda I times vector W is equal to vector V, and vector V is the vector that we just got. So let's write this down. A minus lambda I, that's just what it was before. Let's go up here and I'll show you where that comes from. It is right here. So we have 2 minus 1, 4 minus 2, and now we're going to multiply this by W. So I'm going to call the components of W, W1 and W2, and it's equal to vector v, which we just got, and that's 1, 2. If we convert this to an algebraic system of equations, we have 2W1 minus W2 is equal to 1, and then our second equation is 4W1 minus 2W2 is equal to 2. Notice that these two equations are the same. So what I'm going to do is I'm just going to solve this first one for W1. W1 is going to be 1 plus W2 all divided by 2. Now we get to pick what W2 is. Let's see what we can choose so that we don't have fractions. I think we could let W2 just be equal to 1 and everything will work out nice. We're going to let W2 be equal to 1, and that's going to give us that W1 is equal to 1. So we have our generalized eigenvector, vector W, was equal to W1, W2, and we now know that that is equal to 1, 1. And we'll highlight that one. Now in step 5, we can just write down the general solution. Over here on the right, I wrote down what the general solution looks like when we have repeated eigenvalues. Our lambda is up here in the exponent, and then we have our eigenvector v, and then our generalized eigenvector, vector w. Our solution then looks like this. We have x of t is equal to c1 times vector v. Let's go back up here and grab that. It is 1, 2 times e to the lambda t. Lambda was 3, so we have e to the 3t. And now we're going to have a c2, and we're going to have our vector v again, 1, 2. That multiplies t. And then we're going to add on our vector w, which was 1, 1. And all of this gets multiplied by e to the 3t. And there's our solution. Let's now walk through an example where we are going to solve a system of first-order linear differential equations for the case where we have complex eigenvalues. We're going to be finding the general solution of the system of equations dx dt is equal to minus 3x minus 2y, and dy dt is equal to 5x minus y. The first thing that we're going to do is write the system in matrix form. I'm going to start by letting vector x be a vector with components x and y. This gives us the derivative with respect to time of our vector x that has components x, y. And this is going to be equal to minus 3, minus 2, 5, minus 1. That's our matrix made up of the coefficients, if we look back up here, from our system of equations. And then we multiply this by x, y. We can then write this as the derivative of vector x with respect to time is equal to a matrix A times x, where we're going to define matrix A to be minus 3, minus 2, 5, minus 1. In step 2, we are going to find the eigenvalues of our matrix A. There's our matrix A. There are two ways that we can do this. We can solve the determinant of A minus lambda I is equal to 0, or we can solve the equation lambda squared minus the trace of A times lambda plus the determinant of A is equal to 0. Let's solve the one on the left first. We have our determinant A minus lambda I. That just means that we're going to subtract lambda off the main diagonal elements. And we're going to set that equal to 0. This gives us minus 3 minus lambda times minus 1 minus lambda minus minus 2 times 5. That's just the main diagonal elements multiplied minus the off diagonal elements. This gives us lambda squared plus lambda plus 3 lambda plus 3 plus 10 is equal to 0. So we have lambda squared plus 4 lambda plus 13 is equal to 0. Before we solve this, let's go over here on the right and look at finding our quadratic using this formula. We have lambda squared minus the trace of a. The trace of a is where you take the main diagonal elements and you add them. So this is minus 3 minus 1 times lambda. And then we have the determinant, which is the main diagonal entries multiplied. So that gives us a 3. And then we have a minus the off diagonal entries multiplied, which is minus 10. So this gives us lambda squared plus 4 lambda plus 13 is equal to 0. Now let's go ahead and let's factor this. I'm going to go back over here to the left. Let's first look at the discriminant. Our discriminant here is b squared minus 4ac, and that's going to be 16 minus 4 times 13, which is 16 minus 52, which is minus 36. So this is negative, which means we're going to get complex roots. So we don't have to worry about factoring it. Let's just use the quadratic formula. Lambda is equal to negative b, so that's minus 4, plus or minus the square root, b squared minus 4ac, but we already computed that, and that was minus 36. So we have a minus 36, and we divide this by 2 times a, which is just 1, so that's 2. This gives us minus 4 plus or minus 6i, all divided by 2, so we get that lambda is minus 2 plus or minus 3 times I. We'll highlight that because those are our eigenvalues. And let's just make a note that we have complex eigenvalues. That's going to tell us the form of our general solution. In step 3, we're going to find the eigenvector associated with our complex eigenvalues. The nice thing about having complex eigenvalues is we only have to find one eigenvector. We're going to find it by solving the system of equations a minus lambda I times vector v is equal to 0. Let's remind ourselves what matrix A is. It was the matrix minus 3 minus 2, 5 minus 1. And I'm just going to arbitrarily choose that vector v is equal to AB. Let's now go ahead and let's set this up. A minus lambda I is going to be minus 3 minus lambda, minus 2, and then we have 5, and we have minus 1 minus lambda, and we're going to multiply this by A and B. That's n for vector v, and it's equal to 0, 0. In step 2, we found that our eigenvalue, at least one of them, was minus 2 plus 3i. I think it's just easier to work with the positive imaginary part. Let's now plug this in. We have minus 3 minus lambda, so this is minus 2 plus 3i. And then we have a minus 2, we have 5, and then minus 1 minus a minus 2 plus 3i. And this is going to multiply AB, and it's going to be equal to 0, 0. Let's go ahead and let's clean up our algebra. We have minus 3 plus 2, so that's minus 1 minus 3i, and then minus 2, and then we have a 5, and then we have minus 1 plus 2, so that's 1 minus 3i. and we multiply this by AB, and we get 0, 0. Now let's find our equations. If we multiply this out, we get minus 1 minus 3i times a minus 2 times b is equal to 0. And then we'll go ahead and do the next one, 5a plus 1 minus 3i times b is equal to 0. It doesn't really matter which one of these we choose to solve. They're actually equivalent, even though it's a little hard to tell that because of the complex numbers. I'm just going to choose to solve the first one, and I'm going to solve this for b. So we're going to write down that b is equal to minus 1 minus 3i times a, all divided by 2. To avoid fractions, I'm going to choose to let a be equal to 2, and then we get that b is equal to minus 1 minus 3i. Now we can write down our eigenvector, vector v. Remember that was equal to ab, and this is equal to 2, and then minus 1 minus 3i. I'm going to highlight this because we're going to need that in just a minute. Now we're at our final step, and that is to write the general solution. Over here on the right, I've written down what the general solution looks like for when we have complex eigenvalues. In our solution, we found that lambda was equal to minus 2 plus or minus 3i. So that means that alpha is minus 2 and beta is equal to 3. Let's also go ahead and let's write down our vector v, even though it's right up there. This way we'll have it all together. We have 2 and then minus 1 minus 3i. Let's now look at our solution. Our alpha is up here in the exponent, and then our beta is right here in our trig functions. And then we have our vector v, which is our eigenvector. We have to split it into its real part and its imaginary part. Vector A is the real part, and vector A is right up here, and then vector B is the imaginary part, and that's right there. Notice too that we have a negative sign right there that we have to watch out for. Before we write down our solution, let's write down what vector A and B are. Vector A is the real part of our eigenvector. So that is going to be equal to 2 minus 1. And then B is the imaginary part. Let's go up here to vector V and let's just add on a plus 0i so that we can see that vector V is going to be equal to 0 minus 3. We can now write down our solution. X of t, pull that down a little bit, is equal to c1 times vector A, which we just found to be 2 minus 1, cosine beta t, beta is 3, so we have cosine 3t. Now we watch out for our sign. This has to be a negative. And then we have vector B, which is 0 minus 3, times sine beta t, so that's sine 3t. And all of this gets multiplied by e to the alpha t, and alpha was minus 2. Now we have our second piece, so we have plus c2. We now have vector A again, so this is 2 minus 1. But now we have a sine beta t, so that's sine 3t. Now we have a plus, and we have our vector B again, 0 minus 3. And we have now a cosine 3t. And all of this gets multiplied by e to the minus 2t. Now we really need to do just one more step and rewrite this just so it's a little bit easier to read. We're going to write this as x of t is equal to c1 Now we're going to combine the vectors in our solution. So the first component is 2 cosine 3t. And then our second component is going to be minus cosine 3t minus a negative 3, so that gives us a plus 3 sine 3t. And this multiplies e to the minus 2t. And now hang with me, we have one last part. We have c2. Now we're looking at our second set of vectors, and we're going to combine those. So we get 2 sine 3t for our first component, and then our second component is minus sine 3t minus 3 cosine 3t. And this is also multiplied by e to the minus 2t. And here's our final solution. And that's it. You now know how to solve systems of differential equations using eigenvalues for all three cases: distinct real, repeated, and complex. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.